In this video, we're going to be covering Chapter 6, Section 1, Introduction to Chemical Bonding. Now, chemical bonds are what hold various atoms together because most atoms don't exist alone in nature. They usually exist combined with other compounds in chemical bonds, uh, which are mutual electrical attractions between nuclei and valence electrons of different atoms, meaning it's a way for the charges, both negative and positive, of atoms to connect them on the basis of attraction to one another. And these bonds happen more often than not in nature because most atoms tend to have high potential energy. However, by combining, they can lower their potential energy by storing it in chemical bonds and become more stable, which is the natural tendency to reduce potential energy. So now we'll be covering the various types of chemical bonding, and yes, there are various types. You can't just take two atoms, smash them together, and expect them to stick. But in order to bond, atoms will rearrange their valence electrons. Now, if you'll remember from last video, valence electrons are the ones in the outermost energy level. So let's say this is energy level 1, and this would be the arrangement 1s2, just for review. And then this would be the second energy level, and this would be the arrangement 2s2. So these two here in the second energy level would be what are known as the valence electrons. And the valence electrons are, for the most part, the ones that are involved in chemical bonding. Now, in the last video, we observed that the metals on the left tend to lose these electrons to form the cations, which would make this positive. And the nonmetals that are on the right, so we'll add some more electrons, tend to take electrons in, making them negative. So because this losing and gaining electrons leads to positive and negative ions, what you'll find is that because these opposites attract, these two atoms would bond. I'll give you an example. Let's say you have sodium, which you'll remember is a metal from the right side of the table, which has one electron, and then chlorine, which is a halogen, so it has 7 electrons in its valence. What you'll find is that chlorine is very electronegative, so it'll take this electron off of the sodium, leaving this sodium positive and this negative. Now this is what is called an ionic bond, because, as you can see, the chlorine completely takes sodium's electron and adds it to its own valence, creating two different ions, which then attract, mutually bonding them together. So while this ionic bonding involves sodium completely surrendering this electron to chlorine, meaning it has no more valence electrons, there's an alternate form of bonding, which I'll cover down here, called covalent bonding. Now, covalent bonding involves not electron transfer. However, it involves electron sharing. So, for example, if we had two hydrogen atoms, which each have one electron in their valence, they have one electron in total actually, what happens is that these two will bond together to form H2, and these electrons will whiz around the other atom and their atom that they started with. So basically these two bond together and they share this pair of electrons, which is what happens in covalent bonding, is you share a pair of electrons which can then sort of go around either atom equally in this case. Now, drawing the line between ionic and covalent can be tricky. However, chemists have devised a system, and it involves electronegativity, which we covered in the last chapter, and you'll remember is on a scale of 0 to 4. Now what you do is you take the electronegativity of one element, let's say element 1, and subtract the electronegativity of the next element, and you will get a number x. Now, if the absolute value of x is more than 1.7, the bond is ionic, because as you can see, one will have a much higher ability to attract electrons to it than the other one. However, if it is between 1.7, that is not ionic, and greater than 0.3, what you'll find is that the electron will be shared among the two elements. However, it will tend to favor one. So let's say instead of hydrogen, this was oxygen. Now, oxygen has a much higher electronegativity than hydrogen, so this electron over here from the hydrogen would tend to spend a lot more time over here with the oxygen, leading to a sort of negative pull over here and a positive over here. And this is what we call a polar covalent bond. That is, the electron is shared, however, it leads to a negative pull on one end and a positive pull on the other. And then if this difference between electronegativities is less than 0.3, less than 0.3, what you'll find is that the electron tends to spend almost an equal amount of time with each atom, which means it's a nonpolar covalent bond. Now, just so you get an idea of how to do this, I'll do some examples with math. So let's say we have two hydrogen atoms, which we drew below, each with the one electron. What you do is you take the two electronegativities. In this case, they both have the same, and I know that hydrogen's electronegativity is 2.1. So you subtract them, and no surprise, 2.1 minus 2.1 is 0, which is less than 0.3, which means it's nonpolar covalent. Now let's move on. If you wanted to find a polar bond, let's say you had hydrogen and chlorine. Now, chlorine has an electronegativity of 3. Subtract hydrogen's electronegativity of 2.1, and what you end up with is an electronegativity difference of 0.9, which is, of course, between the 1.7 and 0.3, which means that this is a polar covalent bond. And finally, if you had, let's say, fluorine, the most electronegative element, which is also a halogen, so it has 7 electrons in its valence, and hydrogen, which has just the one, you would again take the two electronegativities, in this case 4, which is the absolute max, subtract 2.1, and you would get a difference of 1.9, which is greater than the 1.7 threshold to get an ionic bond.